Hello everyone. Today I'm honored to be here to share our research. My name is Jingyi, and I'm from Shanghai Advanced Research Institute, Chinese Academy of Science. I'm going to talk about feature detection-based spectrum sensing in NOMA system. The content will be expanded by the following parts, namely background, system model, the proposed methods of feature detection in NOMA, simulation results and performance analysis, and a summary. First, I will talk about the background of our research. In the past 10 years, wireless communication technology has developed rapidly, and the fifth-generation wireless communication network is currently in use. It is supposed to have higher transmission speeds and can handle more complex scenarios. However, for the significant growth of spectrum demands, available spectrum resources are still insufficient. Hence, the problem of how to improve the utilization of the spectrum is a long-term challenge. Spectrum sensing is one of the promising schemes to improve spectrum utilization. It aims to find the spectral idle time of the primary user PU and allow the secondary user SU to share the spectrum whole dynamically. The main methods of spectrum sensing include feature detection, energy detection, and matched filtering detection. Among them, feature detection is a method that can detect the state of multiple users, which is used in this paper. Meanwhile, many studies have shown that non-orthogonal multiple access is a very promising technology. NOMA utilizes superposition coding at the transmitters and successive interference cancellation at the receivers to enable multiple users to multiplex on the same subchannel. Hence, both spectrum sensing and NOMA can increase resource utilization. However, by the definition of NOMA, combining spectrum sensing with it differs much from combining with OMA. How to combine NOMA with spectrum sensing are the problems that we pay attention to. Meanwhile, most of the existing relevant studies regarded edge users as PU, center users as SU, and SU plays the role of relay for PU transmission. These studies have done meaningful work on the combination of NOMA and spectrum sensing. However, there are still lacking research that examines the transmission status of both two NOMA users by feature detection. Hence, to answer the question above, we attempt to explore how to set the sensing threshold under the condition of NOMA. To solve these problems, we have the following contributions in this paper. First, we propose a feature detection-based spectrum sensing technology in NOMA system and design the system framework. Secondly, we varied the feasibility of this scheme. We designed two patterns for detection under NOMA and deduced the relationship between false alarm probability and the threshold. Then we analyzed the performance and compare it with that of OMA. Finally, we have sufficient simulation and then analyze the results. We conclude that the proposed scheme is better than OMA under the same conditions. Now I'm going to talk about the system model. In this paper, we consider the model of downlink NOMA with a base station and two users, as shown in the left figure. We apply cycle delay diversity to generating the feature of the signal. CDD uses multiple antennas to obtain signal feature. The main transmission sculpture is shown in the right figure. We assume that X1 and X2 are the transmitted signals of two users. The power allocation for users is alpha 1 and alpha 2. The first antenna outputs two modulated signals and the second antenna outputs them with different delays. The signals sent by two antennas are both in NOMA mode. Then they pass through release channels and are obtained by the receiver. The received signals are written as this formula. The following are explanations of each parameter. Then let's talk about the proposed method of feature detection in NOMA. Here is the framework of the receiver. We take the correlation between the received signal and the signal after its cycle delay as the detection target. The correlation value reaches a maximum when the delta equals the delay of the users. Take a NOMA downlink model with spectrum sensing as an example. The figure shows the feature amplitude of this situation. There are obvious peaks at the delays of the signals. Meanwhile, at other delay, the amplitude fluctuates within a small range. The following slide is about principle of feature detection. In spectrum sensing, the sensing process needs to determine whether the correlation at the delay is greater than the given threshold, which is a binary decision problem. The received signal can be written as the formula above. The state of transmission signals is denoted as H1, and H0 means the user not to be transmitting signals. Compare the correlation with the threshold lambda. We can conclude that the state of the user. The detection probability PD is the probability of correctly finding the existence of the transmitter, and the false alarm probability PF is the probability of deciding the state of the transmitter to be working when it is not. Thus, we have definitions of PD and PF on the right. Then we make the derivation of the false alarm probability, and we suppose the noise signal and the cycle delay signal are subject to Rayleigh distribution. According to the formula of false alarm probability, we use the properties of random numbers to get the distribution of feature amplitude under a certain delay. Therefore, we get the relationship between PF and lambda as this formula. Details of the derivation can be seen in our paper. Use the formula to determine the threshold of spectrum sensing in OMA sense, and we can obtain the correctness of it. We compare this result of OMA with that of our proposed method in NOMA. The following part is the stimulation results and performance analysis. We suppose strong and weak users share the same transmission state in the NOMA spectrum sensing system. In other words, both users are transmitting signals or neither of them. Because of this limitation, this mode is more suitable for some downlink NOMA scenarios and applications. The feature amplitude of the received signal is calculated and compared with the threshold. Then we use the Monte Carlo simulation to calculate the probability. The basic simulation parameters are listed in the table. In this paper, we use two kinds of modes to calculate SNR. The first one adds the power of the two users as the power of the signal. The other one utilizes the power of a single user for its own SNR, who called with SNR compensation. In order to give consideration to the actual conditions and the fairness of the results, and to give a more complete show of the performance of the system, both methods will be used in the simulation. This figure shows the detection probability PD and the false alarm probability PF of the two users with power allocation rate equals 2 to 1. The user 1 in figures means the strong user, and the user 2 means the weak user. Suppose PF keep on 0.1. Figure A describes that at system SNR, the PD curve of user 2 is clearly below that of user 1. It reveals that when the two users are at the same environment of SNR, the detection performance of weak users will be relatively weak. As we can observe from Figure B, after compensating SNR to their own SNR, both PD of two users are almost superposed with the NOMA result. Then we try to simulate systems with different power allocations. The middle and right figures shows the detection performance with power allocation rate equals 4 to 1 and 10 to 1. It is observed that the less power of user 2 is allocated, the greater the difference between its PD and that of the user 1. And after compensating SNR to their own SNR, in the range of approximately -8 to 0 dB, the detection performance of the two users remained consistent with NOMA. However, when the user 2 is distributed less power at low SNR, PD of user 2 will be larger than that of user 1. To sum up, it can be analyzed that, transmitting with another NOMA user, the performance of user 1 will not be significantly inferior to the NOMA scheme. Meanwhile, the performance of user 2 largely depends on the power allocation. At the same SNR, user 2 is inferior to the user 1 as to the PD. However, at their own SNR, the detection performance of two users is similar to that of NOMA. Therefore, it's better to make the difference between the power of two users as small as possible, due to the inferiority of user 2 at the same SNR. Then, to make the scenario more general, now keep the user 2 signal always transmitting, and we consider detecting the state of user 1. As the two picture on the left indicates, PF start to increase when SNR is -10 dB. We suspect that the existence of the user 2 signal prevents PF from being maintained at 0.1. Hence, we need to adjust the threshold and restore PF to 0.1. While running the simulation, we save the mean value of the signal feature amplitude when user 1 is not transmitting. Now we come up with a numerical solution to adjust the threshold. After threshold adjustment, the curve of PD is still close to NOMA, especially around -2 to 0 dB. The PD value of user 1 is slightly inferior to PD of NOMA, probably because when user 1 is transmitting, the feature amplitude of this simulation is significantly greater than the threshold. Even if the threshold is adjusted, it is still quite small for most feature values in the case of H1. To sum up, the method presented in this paper can solve the problem of PF in the mode of keep user 2 transmitting. Moreover, in this mode with threshold adjustment, the result indicates that the effect on the detection performance of user 1 is not particularly obvious. In this paper, we have investigated the application of spectrum sensing in NOMA system. We have designed the workflow and simulated it to verify the feasibility of the scheme. Considering the form of NOMA, we have designed two modes of spectrum sensing as distinguished the downlink and uplink scenarios in the two modes. Then we have simulated the scenarios and studied the detection performance. The simulation results confirm that the proposed NOMA spectrum sensing technology has good detection performance, which is attractive for practice. Our future work will involve more properties of spectrum sensing based on NOMA, improvements in performance, and further applications. These are all my presentation. Thank you for listening.